Good morning, everybody, and thank you for participating in our virtual and live presentation today. It's nice to be trying to get back to doing professional development seminar series, and we look forward to doing these more frequently real soon. It's nice to have some people live, and it's also nice to have some folks joining us by camera. Today, we're going to talk about diesel rotary UPS systems. Diesel rotary UPS systems are very popular in Europe and are starting to get more and more traction here in the US. I've always been intrigued by the diesel rotary UPS. It has a lot of advantages. First of all, you can put it outside. It doesn't have to go in the building. It also can be delivered at a medium voltage or a higher voltage, 4160 kV or even higher voltages than that. And that prevents you from banging your head against 480 volts, 4,000 amps. So I think as the data centers get larger and larger, the diesel rotary UPS system makes a whole lot more sense. And I'd love to have more engineers take a look at the value proposition that we offer. So without any further ado, I want to turn this over to Ben Jones, coming to us from Houston, Texas, with a great accent for a Texan. Ben, it's all yours.
Wonderful. Hi, everybody. Firstly, thank you for the kind introduction to Scott. I have to say, Scott, I've been working on my accent, so hopefully it doesn't sound so odd at the moment. Anyway, as Scott had said, what our plan today is to introduce you to dynamic rotary diesel UPS, otherwise known as Drups, sometimes referred to as RUPS. There's multiple names. In doing so, what we would like to try and do is compare back to the more traditional type UPS, which is, of course, static systems. And by virtue of doing that, we're going to talk about how the system works. What are the benefits to you guys? How do what we think is completely simplify the one line and actually all of the USPs that Scott mentioned. Medium voltage, very high efficiency, very small footprint. And an outdoor installation, which at the moment is arguably 80% of our pipeline. Before I do that, I do need to talk about HiTec. This isn't a sales pitch, I promise, but maybe again to echo what Scott had said, we have a huge market share in Europe. I'm obviously European. I can tell you firsthand that we probably have 20% market share, which is quite a lot. Quite a big number, as you can imagine, in the data center industry. If you move into APAC, there's a growing dependence on rotary UPS. And that's mainly because of this semicon industry like Intel, Micron, Western Digital, where they're building or almost investing $8 billion into these facilities. And there's 100 megawatts per building, hundreds of megawatts per building. So just by virtue of the technology and our advantages, we're seeing a lot more growth there. But we're not seeing it in North America. And a lot of my presentations like this are more educational. I would hazard a guess to say the majority of people listening might know of Drups, but haven't installed it. There's a minority that have installed it, and then there is the majority that don't know how the Drups works, what are its advantages, how can you install it, where should you install it. And the reason I make this introduction is to say that HiTec aren't an emerging technology. This isn't a new innovative technology that you can install. It's been around for years. We as HiTec have been around since 1894. Our very first machine was installed in the 50s. So we've got over 70 years of portfolio installation that we can talk about. And again, it's not a sales pitch. So maybe to make reference to our other suppliers, there's Pillar, which is more of a rotary technology, not so much the diesel engine. And then what's interesting is there is a third company that recently got purchased by MTU. Now, even MTU, which is a monster, is going to be focusing on Drups. You're going to see a lot more Drups applications, a lot more requests for Drups, just by virtue of MTU's marketing recognition. Branding, it's really fantastic. I actually see that as a really good thing. I think the more people that see Drups and understand it, the better for us, the more opportunities that we're going to have. HiTec themselves are just a critical power specialist. Our roadmap is looking at hydrogen fuel cells and other actually quite exciting technologies to implement into microgrids, as well as, of course, mission critical and other UPS type functions. At the moment, we specialize on Drups, and you can see the photos on the left-hand side. But maybe just to give the last bit of credibility, we're owned by AWI. And AWI is a Japanese conglomerate headquartered out of Osaka, and it's a $7.3 billion company that took us over about a year ago, and we've had some incredible investments. So we're really excited about the future with AWI, what that does for our technology and what that does, of course, for our roadmap. Just to show you where the installation base is, I'd already mentioned that Americas, North and South America, which is my region, we have the smallest number, which is a shame. There's no real rhyme or reason. One might suggest that static UPS, which is about 95% market share, dominates the Americas, mainly because of production, mainly because of the competition is here. All of the rotary diesel UPS suppliers are European. You would have seen on the last slide that HiTec are based out of the Netherlands, about 2 hours from Amsterdam, so it's always a fun trip, as you can imagine. But mainly the installation base is Europe. But that's also because we've been doing it for 70 years. APAC, that 670 units has grown an unbelievable number over the last few years. And by the way, that will soon take over Europe. So incredible number of units. Last year, we as HiTec and many of our competitors, again, this isn't a sales pitch, saw, surprisingly, our best year yet, despite COVID limitations, despite not being able to get face-to-face. But we saw a lot more opportunities. In fact, CCI supported us in one of those projects in California, which is a semicon, 25 megawatts. Again, just another really exciting opportunity. And then there were many other 1 or 2 megawatts, 1 or 2 machines in containers, industrial manufacturing, whatever they were. And lastly, before I move on to the technology, which is, of course, why we're here, I just wanted to give you a quick overview to our footprint. We in North America do have 3 regional support centers, 1 on each coast and 1 in Montreal. We recently opened HiTec Brazil, which, by the way, as I mentioned, is under my territory, is a fascinating market if you haven't been. It really is quite incredible. Mission critical applications popping up everywhere. The dependence on UPS, of course, is that much greater, mainly because of quite a poor electricity grid. So we're seeing some really exciting opportunities there. Then, of course, if you can see Europe and APAC, if you have opportunities, HiTec can partner with you, and we can be that one source for you guys through CCI. We have service centers, we have distributors, we have installation means. So we can take that full turnkey package and deliver globally. So, introduction to Drups. As I mentioned, Drups is just the abbreviation. We use it because diesel rotary uninterruptible power supplies is a bit of a mouthful, as you can imagine. So you might hear Drups, Dups, or Rups. They all mean pretty much the same thing. They mean that you're no longer storing energy in a battery. And so, as I mentioned at the beginning, I'm going to make reference to how we compete to a static. And we have loads of other white papers and presentations where we can compare to supercaps, or we can compare just to rotary, just a pure flywheel, or hydrogen, which seems to be a new technology for mainly for hyperscale. But in this instance, we're going to compare to what we believe has the major market share, which again is static UPS. Moving forward, I'm going to show you a couple of one-lines, but really the one difference, or the only difference you might argue, is how do we store energy? How do we go from a point where the input breaker has opened because we have a problem? We have a mains detection relay that said 0 volts, or the supply is just bad, whatever that might be, poor power quality, high harmonics, spikes from lightning strikes, whatever it is. From going to that, from that supply over to a diesel generator. Typically, with a static UPS, you use a battery. It's an electrochemical device. Very good technology. I would suggest below 1 MVA, we actually will struggle to compete. Very honest. They're really that efficient. The price point is very, very good. And so what we tend to find is above the 1 MVA, above the 1 megawatt mark, I should say. That's where we start to offer all the USPs that I'm going to talk about. We don't use batteries, as I'd said, we use a flywheel. So instead of storing in an electrochemical device, we have a moving part that rotates. And as it rotates, it stores kinetic energy. Nice, simple analogy. If you imagine your push bike, as the wheels are spinning, the faster you go, the more energy you have. The bigger the wheel, the more energy you have. Or the heavier the wheel, the more energy you have. But we all agree that if the wheel is spinning, it has energy, it has kinetic energy, maybe through inertia. Some of the advantages of the flywheel-based system is that it has a 30-year design life. And towards the end of this presentation, I'm going to show you a picture of Hershey Park, which was installed with HiTec in 1986, and it still runs today. And that's a huge testament to the technology. That's 35, 36 years old. Fundamentally, the flywheel has no electronics. It's just a moving wheel. There's not much obsolescence. There's not much there that can limit its life. It's incredibly reliable. It just sits there and it just spins. It has nearly infinite duty cycle. By that, we mean if there are lightning strikes, if there are multiple charges or discharge events, it doesn't affect the life because it's a flywheel. So if we use that flywheel multiple times, there's nothing there that can stop it. The same applies to temperature. There's not the same bathtub curve that might limit the life of the flywheel like that of, say, a battery. So again, this is just all credibility to a very high reliable, very long life machine. NFPA 855, the third one down, that's probably a newer application that talks about limiting footprint around the batteries. I think lithium-ion batteries, actually, mainly because of fire protection. So that's not applicable for us. It's incredibly power dense. So on the fourth item down. Now I'm going to talk to you today about 2.8 megawatt, 2.9 megawatt, which is our highest power density machine. And that sits inside a footprint of about 5.5 foot by 14 foot. If you can imagine now a 3 megawatt or say 2.9 megawatt battery installation, it really is taking rooms upon rooms of batteries, each with their own air conditioning. So I would argue the greatest advantage, if you take nothing but this away from the presentation, it is knowing that a diesel rotary UPS offers by far the smallest footprint of any UPS on the market. And then, of course, the very last one, it's a valued engineered solution. So it's a mechanical coupling. And that's why, for many who joined the presentation, you saw the title, which was, we mechanically integrate a UPS into a diesel generator. So it's a very compact, very simple design. Just to go a little deeper, and by the way, this is still very high level. My apologies for those in the audience who are used to looking at one lines in a much more detailed view. But just as on the face of it, we have a static UPS. And in doing so, we have pretty much always the possibility of poor power quality. It could be anything: harmonics, power factor correction, voltage sags, which is, I believe, 65% of all events when it comes to power quality. Regardless of what it is, if you don't protect your critical load, that will ultimately cause damage or failure downstream, and the severity of which might justify a static UPS or a diesel rotor. In this instance, we're showing that we do have a UPS. And on halfway, we have our rectifier, we have our inverter, and we have our batteries that I just spoke about. By virtue of a static UPS, we take that poor power quality, we rectify it to a DC voltage, we float charge our batteries, and then on the output of the inverter, we artificially create a waveform so that we can feed the consumer load with a nice clean power. And the idea here is that the batteries that are float charged will, of course, provide that interim amount of power until the diesel generator, which I show here upstream as the MTU, gets to speed. Because this diesel generator is off, it's doing absolutely nothing. It's preheated, it's pre-lubricated, and it will get to speed in about 10 seconds. Via the ATS, once the diesel generator has sped up to 1800 RPM, we will then supply power. But if you all agree with that idea, that very high level idea, then you also agree that the batteries are pretty much supplying a transition of power from the utility failing or the utility just being poor power quality over to the diesel generator. The diesel generator, therefore, is providing the long-term support to your critical load, and it will do that within, like I said, 10 seconds. It might be longer, but typically it's 10 seconds. And in that instance, you also agree that providing an alternator spins at 1800 RPM, you are okay. And I say that because in this instance, the diesel generator, when it is stabilized, it is at 1800 RPM. And that is a standard 4-pole machine, 60 hertz, 1500 RPM for 50 hertz machines. And in doing so, once the alternator is at 1800 RPM, the engine has of course stabilized, the clutch is closed. Now, in a diesel rotary UPS, we're slightly different. We're going to get rid of the batteries. We're going to move over to the flywheel. So we're storing energy mechanically. And this is the new one line. Now, the first thing you'll note is the electrical infrastructure as it pertains to the switchgear has not changed. I still have an input breaker, I still have an output breaker, and I still have a bypass breaker. And I can go back a few slides, but it is absolutely no different. The only change in the infrastructure away from the switchgear is the ATS. I no longer have an ATS. Previously, I showed the ATS up front here, feeding my diesel generator. Well, I've moved my diesel generator in this setup. I've moved my diesel generator here. I've got my engine. I've got my alternator. Now, of course, I've added something. I've added a flywheel. And I've added the flywheel because I don't show a rectifier, I don't show an inverter, and I don't show a battery bank. Because I'll say it many more times, I don't store energy in a battery, I store energy in a flywheel. I have now mechanically coupled my flywheel, which is my storage device, to my diesel generator. And so just by virtue of that small change, I've already simplified the one line. As I said, I no longer have the ATS. I don't have my diesel generator here. I don't have the rectifier inverter. I don't have the batteries. And I don't have the air conditioning that goes along with those electronic components. I have added a line reactor. And a line reactor is really only allowing me to tap into the system. Very much like an ATS. An ATS allows the diesel generator to supply load. It switches across the primary and the secondary. The choke is a little different. The reactor, sorry, is a little different. It's more, it's just sitting there. It's just an inline, we call it a choke because of its ability to suppress harmonics and other voltage variations. So as poor power quality comes in, get my words mixed up, it flows across the inductor. And by virtue of being an inductor, it means that we're going to suppress a large fluctuation. So I've already got a nice clean wave. But I'm also tapping into that inductor, and my machine is going to ensure that we have a really nice clean sine wave. Now I'm going to come back to this slide. It's a slightly different visual in a couple of slides. But before I do that, I want to talk about how the Drups is set up. And we're going to go through each component. And that way, when we next show you the single line, you'll have a much better appreciation of how the line reactor works, how the diesel UPS works, how do we get this nice clean sine wave, and what are the USPs. Before I do that, just on the side here, maybe going back 20 minutes at the beginning of the presentation, again, huge footprint savings. Just by virtue of the one line, you can already see the footprint savings because we got rid of the batteries and everything else. In addition to something that Scott had said, we see a lot of medium voltage applications. I can do medium voltage direct generation. I have no need for transmission up or down. This can be a 15 kV source. I will just supply you a 15 kV alternator. These are 15 kV breakers. And so for many applications, we're doing solutions at the substation. We're in fact backing up the entire building. We're no longer isolating what is IT and then segregating maybe mechanical. We're saying back the whole building. And of course, it's much easier when you have the flexibility of doing that at the native voltage, which in this instance could be 15 kV. I'm getting a question, I believe. One other thing I should note, in Loudoun County, in Virginia, most of you are familiar, of course, with Ashburn. They're now moving to 35 kV, which is their predominant distribution. So we, as HiTec, are looking at a 35 kV alternator. By the way, they don't make it. AVK, Morelli, they don't make it. So we are hoping to partner with them and see what that looks like. By virtue of the installation, it's going to be massive. So I think for 35 kV type installations, what we'll probably do is have a transformer between our reactor and our machine. And so for the very high voltage solutions, we will have a transmission. If you go over to California, Silicon Valley, mainly it's 15 kV distribution. So for the project that I spoke about earlier that CCI supported us, it was 15 kV direct generation, 25 megawatts, just a standard parallel redundant. And then finally, we don't need to mix our mechanical or IT loads. Again, we can put it at the substation. And all of this is a very high efficiency of 97%. What I'm not saying is my machine is 97%. I'm saying the system from the input to the output is 97%. And I do have a slide slightly later in the presentation that makes comparison back to static UPS there. They're very much my best guess. So please stop me and correct me where I'm wrong. But you'll see that our efficiencies are very high. So this is a Drups. And for many of you, I would think actually for all of you, you are very familiar with this part of the machine, which is merely a diesel generator. It is a Cummins engine or an MTU engine, even a Mitsubishi, a Perkins, a Deutsch. We can use them all. We can't use CAT, by the way, which I'll explain a bit later. But this is a standard engine coupled to a standard alternator. Again, okay, Morelli, Leroy Samer, it really doesn't matter. We do tend to just use Cummins and AVK, by the way. And it doesn't matter what technology you use. I've made reference to static UPS. If you do need that long-term power, you need a diesel generator. Now, what I've done, of course, or what we've done, is mechanically coupled my flywheel. This flywheel, in this setup right now, is maximum about 2.2 megawatts, which is about 2.7 MVA, and it can go up to 15 kV. This diesel generator is probably 20 feet. And it's the same size diesel generator, whether you were to buy a 2.2 megawatt generator from MTU or Cummins. It's the same size. It's the same components. But what I've done is added this flywheel, which is about 5.5 foot. So now my 2.2 megawatt UPS is within the density of this 5.5 foot machine. Maybe the disadvantage of Drups is that it is mechanically coupled, so I can't put this flywheel somewhere else. So I do, by virtue, increase the size of the diesel generator if you see that as a disadvantage. But of course, the amount of footprint squared is significantly smaller. Also worth noting that a standard, by example, 2.2 megawatt diesel generator, if you were to buy it in a container, is about 40 foot long by about 9 to 12 foot wide. Well, my Drups, also at 2.2 megawatt, will also fit in a 40 foot container, 9 to 12 foot wide. So if you are looking for outdoor applications, I offer significant footprint savings because now I've saved all the room inside the building that would otherwise be allocated to the batteries, to the rectifier, to the inverter, to the air conditioning, to the control panels. So we have this a power block that we call it, which is our container. Now, if you need more than 2.2 megawatts, we can do it. In fact, Drups offers the highest single power density UPS in the world, which is 2.88 megawatts. I show you here. So 2.9 megawatts. Let's round it off. 3.6 MVA. Again, anything up to 15 kV. Now this one looks slightly bigger. The visual doesn't do it justice. We've got our standard diesel generator. This is a much bigger engine than what I showed you before. This is probably a 20-cylinder MTU, by example. We've got a much bigger alternator. Now, that is actually medium voltage, what I'm showing you, because the higher you get in power, the more likely you are going to go medium voltage, just to reduce the conductor size, maybe to reduce the switchgear. Maybe you're limited by the switchgear itself. So I'm showing you a 2.9 or 3 megawatt, let's say, diesel generator. I've got my flywheel that I mentioned earlier. It looks a little different. It has to work a little differently. But by virtue of going to more power, I need more ride through. And I said earlier, if we go back to our example of the bike, the faster that wheel spins, the bigger the wheel or the heavier the wheel, the more energy you have. Now, what we could have done is sped up this flywheel that much more. But if you speed up the flywheel too much, you then introduce mechanical concerns, of course. We could make it that much bigger. We don't want to make it that much bigger because we've got a frame. So all we've done is made it heavier. And we extended it. And so by extending it, we actually make it heavier. We've added more mass. And so for this machine, which again is the 3600, it's slightly longer. This is about 9 feet. The other one was about 5.5 feet. But again, 9 foot long by about 5 foot wide is my 2.9 megawatt medium voltage UPS. Because you already need the diesel generator. You can't get away from that. We've just mechanically coupled it. So again, if you take nothing else other than this away, do know that a Drups is the highest power density and by virtue the smallest footprint of any UPS, not just static, of any UPS on the market. I'd mentioned we can do medium voltage. We can, of course, we can do low voltage. That's our bread and butter. We're seeing a lot more medium voltage though. This middle line around the 12.47 kV in Silicon Valley. We're seeing a lot of 4.16 kV in the Midwest. Of course, now Loudoun County has moved over to the 34 kV. We can do that, but we need a step-up transformer. And so there are still advantages. It just means that we have this extra block, this extra component in the one line. We've done multiple variations of this globally, so we can show you some nice examples as needed. So let's talk about how this thing works. You know the advantages, you understand the setup, but how does it work? Well, in normal operation of a static UPS, what I would be showing is a rectifier and an inverter, and then this would be a battery. And you all know, of course, that rectifier goes to DC and we take it out. We're not doing that, we're slightly different. So in normal operation, I've put my inductor, which is otherwise called a choke. And by the way, the term is interchangeable if you hear choke or inductor in this presentation or in the future. It is just the same thing. The choke references its ability to choke or to suppress large fluctuations. So when you see these spikes or sags, the inductor won't allow it. And that's because it's got a nice magnetic field that it builds up. And so as these enter the choke, it will just smooth it out. So even if I were to remove this synchronous motor that I'm about to talk about, I'm still, just because I have an inductor, I'm still going to have a much cleaner waveform on the output of the inductor than I would on the input. But that alone isn't going to provide us uninterruptible power. That might provide a level of protection against power quality, but it's not doing everything. So the first thing I'm going to do is insert my synchronous motor. And I mentioned earlier, I actually use the choke as a tapping point. So this is actually where I plug in, for a better use of the word. I used to show a plug here on this presentation. I think I might put that one back in. Because if you plug it in, it's effectively got power. And now if I have power into my synchronous motor, the motor will spin. There's a couple of things I have to do to get it to spin, but it will spin. And as power comes in, I have a revolving magnetic field in the poles, and as that revolves, it pulls on the pole of the shaft, and of course, the alternator will continue to spin at 1800 RPM. Nothing's driving it. There's no engine. There's no flywheel. At this point, it's a synchronous motor. And so because it's spinning, it's doing two things. Number one, it's taking a very small amount of energy to do that. Now, an alternator, which has been around for years and years, it's really a perfected design, is about 98% efficient. So I've got 2% losses from this thing just spinning all the time. But because it's spinning, it's supplying power. So now, not only did I have a relatively nice waveform from the inductor, it's supported by my synchronous motor. So now it's like having your own little substation and you have a perfect sine wave. Drups will offer superior load handling above any other UPS, especially static UPS. And this goes back to what we said earlier about mechanical loads, motors and pumps and inrush currents. You have to oversize the inverter. You have to be a little careful with the sizing. I don't necessarily have those issues. I have so much inertia in my flywheel, in my synchronous motor, that I'm going to provide this nice clean wave irrespective of those mechanical loads. It also means because I have this synchronous motor, I'm automatically correcting the power factor because I'm supplying reactive power. So I'm going to have unity power factor on my consumer bus. I'm going to absorb harmonics to less than 2%. Both those generated by the consumer and those entering from my utility, they're going to flow through to my low impedance machine. And of course, I'm going to provide you all the benefits of voltage stabilization. So that's why I say we have this superior load handling. Challenge is what happens when the output at the utility fails. Let's say that input breaker on the upstream side here opens. Well, it's as good as pulling the plug, because when I've lost my power, my synchronous motor will slow down. It's no longer got a source of energy. And if this slows down and the input breaker's open, this waveform is going to be all over the place until a point where you just lose power. So this is fantastic for power quality, but I need something else to turn it into a UPS. Sorry, I spoke about this. We protect against all of the 9 IEEE defined power quality issues by virtue of you having the inductor and the synchronous motor. So I've just changed my symbol. The first thing I have to do is add my engine. So now, in normal operation, my very poor power quality supply is going to turn into a superior load handling supply because my choke and my alternator. If my input breaker opens or if the mains fails, still have a problem. But within 5 seconds, my diesel engine will get to 1800 RPM. And remember, that's what we're doing for a diesel generator. My engine will get there within 5 seconds because unlike a diesel generator, I don't also have to pick up the speed of the alternator. Remember, the alternator was already spinning. But if this takes 5 seconds, I still have a problem because within 5 seconds of my input breaker opening and the engine getting to speed, this is going to slow down. And I just simply cannot allow this to slow down if I want to guarantee clean power, uninterruptible power on the consumer. That's why we had our flywheel. And you'll see back in the photos that we gave you, we mechanically couple a flywheel to the end of the diesel generator. Why do we do it? Well, in this instance, as I said, I've got a problem. My 5 seconds is the problem. Well, I'm storing so much energy in my flywheel that when the mains fails, when that input breaker opens, and I send a signal to the engine, I also start to release the energy that I've stored. And by releasing the energy, I'm transferring it from this flywheel over to my alternator to make sure that this never slows down. So after 5 seconds, the yellow item will gradually start to drop, again, because it's transferring its energy. But guess what? My alternator, my 1800 RPM never slows down. And it will do that for 5, it will do that for 10 seconds. I only need to do it for 5 seconds because at such time the engine is now at 1800 RPM and it is nothing more than a diesel generator. Once that engine is driving this machine, it is nothing more than a diesel generator. All the flywheel is doing is providing 5 seconds of energy transfer. It's providing that bridge, that gap from utility failure until the engine can become the prime mover. Now, to show you a visual representation of speed, we have 3 distinct possibilities. We have the utility being available. Now, when the utility is available, you know the alternator is plugged in. And so you know the utility is spinning that alternator. It's in motor operation. Okay? It's going to spin and it's just going to sit there. The engine is off. The engine doesn't need to be on because the alternator is being spun via the utility. And my flywheel is fully charged. Stealing a terminology from batteries, it's fully charged. It's at 4200 RPM. At 0 point, so we have a problem, utilities failed, the input breaker's open, quality issues, whatever it is. My flywheel slows down so that the alternator doesn't. That's the fundamental premise. As long as this alternator spins at 1800 RPM, you have power. So as this slows down, my engine speeds up. Within 4, it's actually 5 seconds, the engine will stabilize. Now, interesting note, the actual engine will start within 2 seconds. It's a bit like your car. You start the ignition, it's on. But it does take time for the turbo lag to stabilize. It takes time for everything to stabilize. So after 4 seconds, maybe you'll start to introduce load, but really after 5 seconds, when the turbo lag has gone, you can put 100% load on the engine, you shut the clutch, and then of course the engine is driving the alternator, it's a diesel generator, that flywheel will speed back up and it will get to this 4200 RPM mark and it will just stay charged. And it will do that time after time after time again. We're not worried about the discharge cycle, we're not worried about affecting the life. When the utility comes back, after predetermined time, whatever the circumstances might be, we will just simply synchronize back to the utility, which I'll show. I think I've got a slide. And that's it. It's just a seamless transition from synchronous motor to synchronous alternator. And to get a little bit deeper, this is how we do it. So, you know that we mechanically couple a flywheel to the end of the diesel generator. So I'm not showing you the diesel generator here. The end of the alternator is here. Now, a standard diesel generator has the exciter and everything mounted on the end. We don't do that. We actually have an open end. We actually have the end of the shaft open to us, and we connect a flange. And so what we do first and foremost is we connect this shaft to the alternator shaft via that flange. Now, if the alternator is always spinning at 1800 RPM, then where we connect to it is also spinning at 1800 RPM. It has to. So anything that's yellow in this photo is spinning at 1800 RPM because it's connected to the synchronous motor. And when the mains fails, what we've said is we need to transfer the energy from the flywheel to make sure that 1800 RPM the 1800 RPM that's spinning never slows down. We do that by spinning this inner drum. This inner drum is the flywheel. It spins quite a bit faster, 2700 RPM faster. Relative speed is 42. We have a pony motor, which controls the speed. So, by the way, this is variable. So if you have low load, we'll slow it down. Customer preference. And that means at part load, it's more efficient. So we have a pony motor that controls this drum. And this drum is free spinning. I've got bearings here, and I've got bearings here. So it's completely free spinning from the rest of this machine. In case of a mains failure, I inject a DC current into these windings. Simply what I'm doing is creating a magnetic field. And in layman terms, I'm creating a magnet. And as I create a magnet on this yellow, so it's 1800 RPM winding, it is effectively breaking the inner drum that's spinning much faster. So as that yellow device spins, it pulls on the pole of this inner device, and every time it passes a pole, the magnet will continue to spin. So ultimately, that magnet means that my 1800 RPM will spin indefinitely, or until at least this flywheel slows down below 1800 RPM. So it's just by virtue of a magnet that we're pulling the energy from the flywheel to ensure that the 1800 RPM doesn't slow down. Now let me go back here. As I create my magnet, the strength of the magnet is an interesting metric. If I create a really, really strong magnet, then what could happen is the alternator will speed up because it's trying to catch the device that it's pulling on. Now the device it's pulling on is spinning that much faster, so they could speed up. If I don't put a magnet that's strong enough, if the electromagnetic field isn't strong enough, then the alternator might slow down a little bit. This might level out a little bit. So the amount of electromagnetic field is via a controlled DC current. That controlled DC current is fixed, and it allows us to perfectly control and to make sure we maintain our 1800 RPM. This 42 drops to 41, 400, 39, 38, whatever it is, until the engine takes over. So we're going to go back through. And you've seen this one line, you understand this. We've got our standard switchgear configuration, input-output bypass, very similar to a static UPS. As active power comes in, of course, it has poor power quality, potentially. It flows across my inductor. Now, my inductor is very low reactance, and it's connected to my alternator, which is very low impedance. And so the combination of those two allows me to provide a perfect sine wave, superior load handling, free of harmonics, free of power sags, surges, whatever the transients might be. You're going to get this very nice, clean sine wave. I'm providing reactive power because my synchronous motor is spinning. And in this scenario, in normal operation, let's hope 99.9% of the time, my engine is off, my clutch is open, because I don't need the engine to drive the alternator. Remember, it's in synchronous motor. And my yellow device is charged. It just sits there via my pony motor and spins. This is about 98% efficient. Sorry, let's do it another way. This is 2% losses. This is probably less than 1% losses, or it is less than 1% losses. I have a couple of losses from my inductor, but overall, the system efficiency here is 97%, give or take. I don't have air conditioning to talk of. Like a normal diesel generator, I have air. Air is my cooling medium. So imagine a diesel generator container. I have ventilation, air coming in, air going out. I have a radiator. Nothing special. Quite simple. If the mains fails, then my input breaker, and by the way, HiTec can supply the turnkey, which means we can do the switch gear, We'll do all the switchgear specification. We can do the mains detection relaying. We can do it all. We actually have an engineering team here in Houston that focus on that, as well as a project management team and a service team and a sales team here. But when the input breaker opens, my alternator was already instantaneously at 1800 RPM, which, as you know, is the speed for a static UPS that you wait for the diesel generator. I'm not waiting. My alternator was already there. Challenge is to maintain it. That's why I release my flywheel. At the same time, my engine starts, and then after 5 seconds, it's a diesel generator. The engine got to speed. The engine clutch closes. It's now the prime mover of the alternator, and nothing changes. From this moment in on out, you understand the system. You know how diesel generator works. What are the benefits? Well, firstly, this is Hershey Park. And if you look at this, most of you will be able to pinpoint some pretty obvious components. We have the engines, we have the exhaust, the engine batteries, the alternator in the back here, the UCP. This is actually the fuel system. The reason I go through that is because this is 35, 36 years old. And by virtue of my technology, which is incredibly efficient, very reliable, it's been around for years. I actually needed to figure out when the alternator was built. I need to get that year in the 1800s, I'm sure. So the design has been perfected. We don't have obsolescence issues like electronics. If you imagine your phone 10 years ago, very, very different. And in another 10 years, I'm sure it's going to be very different. So the rate of technology change means that electronics will naturally be replaced. We don't have that issue. Engines, alternators, they've been around for a very long time, and they will continue to be around for a very long time. Efficiency, something that we spoke about. My system efficiency is 97% efficient, and I'm more than happy to talk about the individual losses. What are the parasitic losses that get me to that 3%? And we can do that offline. I can send you based on your preferred size. Comparing back to a static UPS by example, we have losses from our battery. Our static UPS is 97. I might actually be a little low, 98 maybe % efficient. But you also have losses from the air conditioning. You also have losses from the diesel generator, preheaters, pre-lubricators. It's not on, but it's not completely cold. It has to be preheated. There is energy that's required. When you take in all these losses, you get to about 93% system. Now, again, I might be slightly biased. I don't believe I am. I think the biggest unknown is the air conditioning. Even if this were more efficient, it's very tough to get a system efficiency to 97. But I am more than happy, as I said, to show you our losses. You can do that analysis yourself. Of course, we'd love to help. But this is what we see in the market today. And if you look at why that's, of course, important, well, the bigger the power, the more OPEX comes into play, maybe. I'm using 10 cents. It's probably not fair for Atlanta. I recently did a couple with CCI where it was a lot lower than that, I know. So, again, more than happy to change. This is just based on a generic presentation that we offer across the US, and that's why we fixed to 10 cents. But needless to say, it's a huge OPEX cost saving, which you can offer on to your customers. So it's not just the engineering, it's not just the footprint. It is also, of course, the OPEX savings. And by now, you'll all realize the footprint savings are massive. And I'll say it one more time. If you take nothing away from this, please remember footprint savings are everything for Drups. Because whether you go Drups or static, you need a diesel generator. And this is the diesel generator, and I show you the two components that I've referenced throughout the presentation. What I've done, however, is just added my flywheel, and that flywheel, which is 27 foot squared, the size of a table, at 2.2 meg is your rectifier, your inverter, your static, your batteries. And if you consider NFPA 855 in California, you then have the space between the individual battery racks, which I think is for fire code, which further requires more footprint. So again, huge footprint savings and simplicity of design. Now, going back to where we had earlier, I showed that one Drups, input breaker, output breaker, and bypass. If you remember a standard diesel generator configuration, you have multiple in parallel. I can do the same thing. On a single input board, a single output board, I can parallel 1, 2, 3, up to 20. We've done 25, I think 26 in Asia. And so by paralleling in a standard parallel redundant configuration, I can have 4 machines to make, by example, 8 meg, 5M plus 1. We can do distributed redundant. We can do IP bus. I got slightly off topic. What we're talking about on the slide is critical versus mechanical. And with a Drups, you're not worried. I don't just have to isolate my IT. I can do the fans, the cooling, the lighting, the pumps, the motors. Now, don't get me wrong. I'm not saying I won't derate it. The vast majority of the applications we look at, we don't derate because they're VFD or soft start. But we do have customers, one specifically in the Carolinas, no longer. They actually they moved facility. It was Michelin, and they had old direct online 6 times full load current. So yeah, there are applications we might have to look at it, but for the most part, we're not so concerned as you would be with the limitations of an inverter. And this is a project we're just commissioning now. This is going to Austin. We're really proud. We just released a case study. Despite the crazy weather that we had, and by the way, I'm in Houston, so I can say that firsthand. We lost power for 4 days. It was just a nightmare. But all our machines in Texas ran perfectly. Our customers were very happy. We had our support team on standby. We actually put people there in advance, so we were very proactive with that. And this is the 3rd unit for that customer. It's containerized. This is custom, so it's a little bigger than the standard 40 foot. But in this instance, they've got a really big bulk tank at the bottom here. The container sits on that bulk tank. So what will happen is we're testing at the facility. I think this is Gertz, for those of you that know them. They build the frame, they build the walls, they insert the Drups, they put the roof on top. We do our function test. We then actually remove the Drups, which is odd, and we deliver the container as a whole. Of course, depending on the size, we might have to do 2 shipments, whatever it is. But this is a really nice kind of visual that shows you how we containerize these things. This is a 2.2 meg. This could be medium voltage. It could be 2.9 meg. Again, as I mentioned earlier, standard air in. By the way, if you were to see this, you wouldn't know it was a Drups versus a generator. Air in, air out. I think it's a roof-mounted radiator. We provide the small power. We do the lighting. We've obviously done the fuel system. And that was custom turnkey by HiTec. So, from your perspective, it very much is a single partner. We have all our suppliers. So coming towards the end, a couple of installs to talk about. And again, it's not a sales pitch. There are others. MTU will have theirs. Pillar will have theirs. I just want to give some credibility to installations so you can see what we've done more recently. Most of these are within, I would say, the last 5 years. IBM Kojika is a data center. You can see it's medium voltage, thicker conductor, much wider alternator frame. But direct generation 4.16 kV. I actually think they take that all the way to the rack. So they're quite focused on PUE. And so by taking it all the way to the rack, I think for them it provides a level of efficiency. There are 6 of these machines, distributed redundant type configuration. Sanofi Pasteur is a really good one for us. They're a pharmaceutical that specialize in vaccines. And of course, the most pertinent is COVID. So we do supply that facility. It's in Toronto. A very heavy mechanical, pumps, motors. It's a pharmaceutical facility. So very little IT, actually. A lot of safety, a lot of fire. So we're very, very proud of that installation. AT&T Redmond Communication, of course, containerized solution here. This is a double wide. There's 2 machines per container. Very small footprint. I think this is 40 foot by 15 foot. That's why we have high level air in and out, and the radiators on the roof. Bristol Myers Squibb, again, yet another really exciting. This is in Puerto Rico. I'm sure many of you know Puerto Rico get hit really hard every year by hurricanes. Constantly power cuts, constant power interruptions, long-term outages. We're very proud that we supply this system, and despite those, we've constantly supplied power. We've obviously done maintenance when it's been off, but we've never had that catastrophic issue. And then you go to Asia, and it just gets silly. Singtel data center, they've got, I think in total, we show 10 here, but I think in total there's 30. There's 3 banks. Huge power at demand. And you can see just in the back, the old legacy machines. So the Power Pro that we talk about installed in 2015. That's when we released that new product. But again, huge testament that people are coming back to us. Another semicon facility, again, Asia. Just to show you indoor installations. They don't have to be containerized. This is actually on the top floor in Singapore. Again, we did the whole thing. Turnkey install, acoustics, air ventilation, the whole thing. And then I think finally, I believe this is the final one. So for those of you that are interested, we'd love to present more. We'd love to take this and do a lunch and learn. Maybe CCI can support us there. But if you have the opportunity, we want to invite you to Amsterdam. We've done that now together with CCI, with other customers. Not just Amsterdam, I should say. We actually want to go to the factory, but of course, Amsterdam's always a good stop. And the factory is where you get to see really how this thing comes together. We have the test bays. You can see the assembly plant. This is a photo from the assembly bay. But before you go, you get to see one in operation, I hope, because Amsterdam Schiphol Airport has Drups, has HiTec Drups. And we back up the entire facility. But more importantly, AMS Schiphol is home to the European Air Traffic Control, the whole of the European Air Traffic Control. That is an incredible mission critical application powered by HiTec power protection. And we're very proud of that. So you get to see this machine in all its glory. Are there any questions?
Guys, if anybody has any questions, you can pull them up in the chat.
I was just wondering if, if these units have to meet, I guess design requirements that other generator manufacturers like UL 2200, or do you offer tier 4 emissions, things like that, seismic?
So basically, it's regulatory control the same for a Drups as it is for a standard diesel generator engine.
Right.
Yeah. Okay.
Yeah, really good question. The answer is yes and no. So for seismic, yes. We do a lot in, as you know, Japan and such things. They're all on that seismic belt. And so on the bottom of the frame, we provide vibration dampeners. But we also can provide special seismic vibration dampeners for California, for Japan. They are compliant to all of the required code, California, Japan, whatever it is. So that's a tick in the box. For tier emissions, yes, typically tier 2. If you're moving over to California, tier 4. If you want to export power, so you're no longer just standby, which is a true diesel generator. If you want the ability to export power or island, you need tier 4. We do it all. I didn't talk about it, but Bristol Myers Squibb, the one that was the blue container, the double wide, that is tier 4. That was designed by our suppliers, and so that's all the urea, particle filters, anything that we do. And we also, by the way, get it verified to tier 4 emissions, so we can do all of that. UL, no. UL 20, I think I heard you say 2200. That is specific for diesel generators. We have our own UL code, but there's no UL stamp. And so part of our offer is to get the system UL verified The difference between certified and verified being, as part of our scope, we hire a third party to come in and to rubber stamp it. And then you have a UL system, but you just won't get the UL stamp. It's not a component stamp. So it doesn't mean anything for you. You still have your UL requirements.
Ben, we got a couple questions in the chat. One from Russ. How long will it take the flywheel to get back up to full speed after an outage?
It's about 8 minutes. And the reason being is the diesel engine, just to give you nice round numbers, if you've got a 2 meg system, you've got probably a 2.2 meg alternator because you need to allow for the additional losses. And you've probably got a 2.2 meg, 2.3 meg engine. And so what we don't want to do is oversize the engine so that we can charge the flywheel that much quicker, because it doesn't provide us value. We can do that. If you specifically want the flywheel charged quicker, we can oversize the engine, but typically it's 8 minutes. I will also say that when you go into diesel engine operation, you're probably good leaving it for an hour. Leave it as a load test. Leave it as a run test. Let that engine clear itself out. Each to their own. The second the mains detection relay says it's good to go, and providing the flywheel's charged, we'll synchronize back.
Excellent. Second question. You're relying on a generator to start in less than 10 seconds. What if it does not start? We had issues with a large gen not starting up until 60 seconds.
I don't know the context of why it didn't start within 60 seconds, but under the NFPA 110, I think it has to start in 10. Now, you're right. If it doesn't, it doesn't. Okay. Typically, if an engine doesn't start for us within 5, it's a fuel system problem, because we have redundant batteries. We have redundant battery starters. If you don't have fuel, then it's not going to start within 10 seconds. But the reason I say that is because if you don't have fuel, your diesel generator is not going to start. And so your batteries in a static UPS, as a comparison, might give you 5 minutes, but you're not going to be able to get a diesel generator tech there to fix it. So you have 4 minutes and 50 seconds to panic. But it's a great question. That is the only thing I can think of, which is why an engine wouldn't start. In the scenario of this, you didn't get it up to speed within 60 seconds. I also want to note that in a Drups, the alternator is already synchronized. By virtue of it being in synchronous motor over the synchronous alternator, we're not synchronizing the alternator. And I would imagine that's why it took longer for the 60 seconds, but I don't know. So I hope I'm not jumping to conclusions.
That's great. Third question, how does Drups handle voltage regulation?
Perfectly. So it is the combination of the inductor, which is in line, coupled to the synchronous motor. And remember, the inductor's low reactance, the alternator's high at low impedance. And it's the combination of those two which will ensure that on the output of the inductor, on your consumer bus, we meet at minimum SABIMA. And so typically dynamic voltage variation is plus or minus 1%. In a load step, in a short circuit, 10% max for predetermined time. But we are within the envelope of the SABIMA.
Excellent. One more. How steady is the frequency? I'm used to gensets not being so stable with voltage and frequency.
Two scenarios there then. So frequency regulation in normal operation is simply whatever the utility is, because the synchronous motor won't correct the frequency. It's a line interactive type UPS, not a double conversion. So if the input frequency drops below our plus or minus percentage, which is plus or minus 1%, the Drups will take over. The actual question was in diesel operation. I have to say, I've been doing this for 17 years, and it's very, very rare that in diesel operation, at least for me, that the frequency has been a question. So I'm going to reach out to my service engineer, my service manager next door, and find out. Maybe I can give a more comprehensive answer. But in my experience, that's not been a problem. So it's just not a great answer for you. So I'll take that away.
What kind of maintenance is needed for the HiTec components, excluding the generator?
Great question. There's three components. The flywheel, it spins. It has automatic lubricators, automatic oil and grease lubricators. So no maintenance. You have to make sure the pot is full, but there's no yearly maintenance. On the 10-year mark, I have to replace the bearings. The generator also has the advantage of sharing the automatic lubricator. So that also has no maintenance other than the 10-year, where we replace the bearings. There is an earthing brush, which is designed to remove eddy currents from the shaft, because eddy currents can pit on the bearings. And so that, I think, is changed every 6 months to a year. But that's doesn't need to be off. You just change it. And then the last thing is the engine, and that has standard engine maintenance every year. Oil, filters, change of oil, air filters, fuel pre-filters, and that's it. Our maintenance contract is we turn up every month if you choose. Every 6 months is our standard, just to give it a clean, and then every year. And it's very minimal. It's really the 10-year is the major.
How long does it take to change the bearings, Ben?
It's about 4 days, but that's not really a fair answer, because if I were to have a flywheel, a kinetic energy module done and there, it's much quicker. But 4 days is probably good every 10 years.
Okay. One more. Is there any load concerns when it comes to the type of load in your specifying system when you're specifying your system?
Leading power factors, yes. If you're outside of a 0.8 to a 0.8 window leading to lagging power factor, that might be a concern, but very rarely do we have leading power factor. If you have old motors, pumps that are direct online, so they're 6 times full load current, yes, that probably introduces the problem. But for the most part, no. We've got examples and case studies of all types of loads, quite dirty mechanical loads, very high harmonics. You know, we can, I'm getting into too much detail here, but if you have a system that's really heavy harmonics, we can actually change the impedance of the alternator and the reactance of the choke to accommodate that. So typically it just requires us to know, but I can't think of many scenarios.
We got one more. How many techs, or how do you handle emergency service in the US if the system fails?
Great question. By virtue of our install base, typically West Coast, East Coast, we have offices. So we have satellite offices in Concord, which is the Bay, and Virginia, which is for Ashburn. But that's not all our install base. So we have them in the Midwest. In total, we have 15 service techs that are direct employees. We also have partners, service partners in other regions. Typically, if you have a customer that, say, has 4 machines or more, we will probably allocate a resident engineer if you don't have the advantage of any one of the current techs or service partners. As for response, I would argue 95% of our contracts are 4-hour emergency response. We also have a help desk, which is a 24-hour manned hotline globally. And you call that at any point, you get your answer. To actually have a man, again, might be 4 hours, it might be 8 hours, but we can build that into the contract. So,
excellent. Thank you, Ben.
Yes, thank you very much, Ben. We appreciate you taking the time, and we appreciate our guests coming. We look forward to doing another PDSS very soon. If anyone wants to participate or present. We're always looking for topics that we can present or something that you would like to present on yourselves. Again, we look forward to having more and more people in attendance with spring coming and vaccines coming. We look forward to a lot of good things to come, and happy spring to everybody. Thank you for joining us.
Wonderful. Thank you again. Appreciate the time.